So in this video, we're going to go over the idea of a projection of one vector onto another vector, or in this case, the projection of u onto v. So here's the definition of the projection of u onto v, but instead of reading this, I'm going to just go kind of into a picture explanation that I hope will make sense. So let's say I have a vector u, and down here I have a vector v. And here I drew it with an acute angle, but I could just as easily have drawn u and v to be two vectors where they form an obtuse angle where they meet. Let's see if I can, maybe I can't draw it just as easily. So here's vector u, here's vector v. So the idea behind a vector projection is simply this. Take the vector v that you want to project u onto. I want to project u onto v. This is the projection of one vector onto another. So if I want to project u onto v, what I want to visualize is drawing the line that contains v. And this is either for the acute or the obtuse case. I could do it with a 90-degree angle as well, but you kind of get a degenerate case. It's a degenerate case. It's not very interesting. And then what you do is from the terminal point of the vector u, which I didn't draw, you drop the perpendicular to the line through v. You drop this perpendicular. So this is going to be a right angle right here. We drop this perpendicular. So that hits at a right angle. And what this does is decomposes u into two vectors. So let me swap out my pen color. Pointer options, ink color. Let's go over to black. It decomposes it into two vectors. I can start here at the toe of u, the initial point of u, and draw the vector parallel to v, but that goes all the way out to the foot of the dropped perpendicular. And this is, in the definition up here, this is the vector w sub 1. And then we have the vector that is orthogonal to v, that I can draw by starting here at the terminal point of w sub 1 and drawing up to the terminal point of u. And this is the vector in the definition that we're calling w sub 2. So the vector w sub 1 is by definition the projection of u onto v. And if I have the obtuse angle case here, I would still start at the terminal point of u, draw along the line containing the vector v, and then stop at the foot of that perpendicular, and this is the vector w sub 1. W sub 1 is parallel to v, and when you look up at the definition, that's the first requirement. W sub 1 has to be parallel to v. So in both cases, w sub 1 is parallel to v. Then the vector w sub 2 you get by starting here at the terminal point of w sub 1 and drawing up to the terminal point of the vector u. And this is the vector w sub 2. And in the definition, w sub 2 needs to be a vector that's perpendicular to v, which by construction, how I drew the picture, it is. So w sub 2 is orthogonal or perpendicular to v. And because of how we built this, because of how we constructed the diagrams here, it's going to be the case that w sub 1 plus w sub 2 is the vector u. W sub 1 plus w sub 2 is u. So that's kind of by construction. And then we give w sub 1 the name. We call w sub 1 the projection of u onto v, and we denote it like this. So it's going to be more common to see it written as the projection of u onto v. So the projection of u onto v. And then the vector w sub 2 is the vector component of u orthogonal to v. Orthogonal because it's perpendicular to v. And then you calculate w sub 2 by just taking this relationship here. U is the sum of the two vectors. You subtract w sub 1 from both sides. You get w sub 2 is the vector u minus the vector minus the projection of u onto v. So another way to write this is w sub 2, the orthogonal component of u the orthogonal component of u is just going to be the vector u minus the projection of u onto v. And it makes sense that it would be orthogonal if you think about it. You take and you subtract off you subtract from u everything that's parallel to v, you get what's left is going to be orthogonal. So here's the vector projection, and the idea is we can calculate a vector projection by using a dot product. That's been what this set of videos has been all about. And so the claim is that the projection of u onto v can be found by taking u dot v divided by the size of v squared times the vector v. And it is kind of important to note that this can be manipulated a little bit. So if I do u dot v divided by, and this is the size of v squared, so if I leave one size of v here, and then I'm multiplying, this is a scalar, u dot v divided by size of v is just a real number, and if I then move the other size of v underneath the vector v, I want to recognize that v over the size of v is v hat. It's the vector of length 1. This is v hat, and the size of v hat is 1, which means the length of the vector is going to be the scalar. So the result is that the size of the projection of u onto v, the size of it, is just going to be u dot v over the size of v. So the size of the projection comes right out of the projection formula. And the derivation of this is pretty straightforward. You just take a vector u. So here's the way to think about it. Here's a vector u. Here's the vector v. And then let's change pen color. So go to pointer options, ink color. Let's switch back over to red. So the vector that when we drop that perpendicular, w sub 2, or the projection of u onto v, is this vector right here. And these two vectors, this guy right here is the projection of u onto v. They have an angle that's formed between them, right? And so what we know from trigonometry is if we had this length and this length, and this length here would just be the size of the vector u, and the length of this vector would just be the size of the projection vector, we could actually calculate the cosine of theta. Cosine of theta, because I have a right triangle, would just be equal to adjacent, which is the size of the projection. There's the side adjacent, divided by the hypotenuse, which would just be the size of the vector u. And then if you multiply both sides by u, you get that the size of u times the cosine of the angle formed there is the size of the projection vector. And then this projection vector is in the direction of v. So a unit vector in the direction of v is just going to be v divided by the size of v, which is our vector we've been calling v hat, the unit vector. So we have a unit vector in the direction of v, and we know how to calculate the size of the projection. So if we want this vector, if we want to find the vector, the projection of u onto v, this would just be equal to the size of the projection, the size of the projection vector, projection of u onto v. Should drop the vector notation to make my life easier. It would be the size of the vector we want times the unit vector in the correct direction. And here we see that we can, the size of the projection is just the size of u times the cosine of theta from trigonometry, times v hat is just the vector v divided by the size of v. And then in a previous video we discovered how to calculate the cosine of theta. We discovered that the cosine of theta is just u dot v over size of u, size of v. So we can replace the cosine of theta here with that. So we have the size of u sitting right here, I'm going to drop the vector to make my life easier. And then it's going to be times the cosine of theta is just u dot v divided by size of u, size of v. And then we're times the vector v over size of v. And from here things simplify a little bit. The size of u divided by the size of u is 1. So I get u dot v divided by size of v times size of v is the size of v squared, which is a scalar, times the vector v. So there's the projection formula. And when we're in this form right here, where we're multiplying by the unit vector, that calculation is the size of the vector. That scalar right there is the size of the vector, which we already talked about.